So let's take a look at the second part of 3.1, which there isn't really much left here. And then we'll spend the rest of the class and tomorrow on 4.1. So what we're going to look at here is basically 6 formulas. Okay? And they're all very similar. And the idea is, we know that inverse sine and sine cancel each other out. It's kind of like if you said take the square root of 9 and then square it. Well, you just did something and then you just undid it. So if I did something like, how do I want to do it first? Let's do the inverse sine of the sine of 25. Right. What should happen is inverse sine and regular sine cancel each other out. And if you're in degrees, that's how you should be doing this. So let's type it in again. And what happened there is it's inverse sine and regular sine canceled out, and I got back the original thing that I typed in. It's kind of like if I typed in the square root of 4 squared. If I hit enter, I'm doing something to the 4, and then I'm reversing what I just did, so I'm just going to get back what I originally typed in. It's the same idea. Now, if I do something like, let's try like a negative number. Sine of, let's do like negative 38, just matter. It worked. I got back negative 38. And what did we say yesterday when we do inverse sine? That you're always supposed to be between. You have to be between negative 90 and 90. Well, let's try typing in a number here that's not between negative 90 and 90. And watch what happens. Let's do 102. This time when I hit enter, it gave me an answer, but it didn't give me back the same answer that I started with. And that answer is not between negative 90 and 90. It's one that I typed in. I got 102. So inverse sine and regular sine do cancel each other out and give you back what you typed in if you type in something between negative 90 and 90, okay? Or between negative pi over 2 and pi over 2. Right, so whatever you typed in right here is exactly what you're going to get back right there. And that's what I tried to show you guys with 25. What I typed in there is what I got back. Typed in negative 38. That's between negative 90 and 90. So I typed that in, got the same thing back. Then I showed you one if you didn't pick a number between negative 90 and 90, like 102. Didn't get 102 back. Okay. So these two things cancel each other out as long as you're between negative 90 and 90. So we're going to look at the same formula for cosine in a minute, and then for tangent. And we're also going to look at kind of that variation of it. What's the difference between formula 2a and 2b? Yeah.
Negative sign is inside.
Yeah, this one's on the inside. What do you call that one again?
Inverse sine.
Inverse sine, yes. So you've just switched the order that you're doing it in. Inverse sine is on the inside. Now, this one only works if you type in a number between negative 1 and 1. Okay, and I'll show you why that's like that. And it's going to tie in a little bit with what we start to do next week. So let's just pick a number and try one that works. Sine of the inverse sine. What's a number I could plug in for x? And if I type that in and hit enter, I'll get that answer back again. How much? 0.5. So if I type in 0.5, 0.5 is between negative 1 and 1. The inverse sine and regular sine canceled out, and you get back exactly what you typed in. Matt, what's a number I could type in? Michael, sorry. What's a number I could type in that wouldn't work? 2. So if we type in 2, that's not between negative 1 and 1. And this time, we don't even get a different answer back. It just says domain error. And because by typing in 2, you basically just tried to do this. Let's go here for a second. Let's graph what sine looks like. Okay, that's a picture of the sine function. Okay, it's a wave. So we'll study more about that next week. But now you said, what number did you say? You said 2. So by plugging 2 in, I got an error because visually what you just tried to do is find where those two graphs cross each other. Where do they cross? They don't, and that's why you got an error. The highest that graph in blue goes is 1, and the lowest that it goes is -1. That 1 and -1 has to do with why this is 1 and -1. It has to do with the graph of sine. Now I did, or what was the first one you told me, Hendrik? 0.5?
Yeah.
All right. Now if I put in 0.5, there's the graph of sine again. And now you're going to see a line at 0.5 in a second. Do those cross each other? Okay, Joey?
Yeah.
Yes, those cross each other. So if you look at it, they cross each other many times. So the problem here is how many answers would you have? There's infinite answers. But we know which answer to pick because we talked about yesterday. If there's multiple answers, you're always going to pick the answer that's between these two numbers. And that way we only get one answer. Okay. So for those that weren't here yesterday, we talked about this -90 to 90 thing. Because if you don't and you use the chart, you're going to get multiple answers for the same problem. And then you don't know which one to pick. Okay. So it just helps us know which one to pick. So let's try this one. So this kind of question is basically either a yes or no. So it's asking if the inverse sine of the sine of pi over 8 would equal pi over 8. So first thing we're going to figure out is if we should be looking at formula 2a or 2b. So Nick, which formula is this one?
2a.
Yeah, it's 2a. How do you know that?
The way the sine's in position.
Yeah, inverse is on the outside. In 2a, it's on the outside. Okay. So our angle here, Larissa, this angle is in what units? It's in radians. So that means we're looking at the condition for this formula in radians. Okay, you can look at it in degrees, it just doesn't help us here. So it's -pi/2 to pi over 2. All right, so think of that on like a number line. Here's 0. Here's -pi/2. Here's pi over 2. You've got to be in here somewhere. The question is pi over 8 in that section that I shaded? Joe, what do you think? Yep, can you explain why? Because sometimes with the fraction, it's a little tricky.
More like pi over 2 degrees.
Yeah, so if you convert it to degrees, you could look at it that way. Also, think about comparing the pi over 2 to pi over 8. Pi over 2 is a bigger number, right? Think if you have a pi and you got to split it between 2 people, you're going to get more than if you take pi and split it to 8 people. So pi over 2 is bigger. So pi over 8, it's still positive, but it's like over there somewhere. So the answer here is yes. That does work. Right, but that is one way you can always do it. If you get confused with the radians, change it to degrees, and then check if it's between -90 and 90. But that's an extra step, so keep that in mind. All right, let's look at this one. Inverse sine of sine of 3 pi over 2, will that equal 3 pi over 2? So the setup is the same as the first one. Inverse is on the outside, regular is on the inside. All right, so Tyler, what am I supposed to be between again? Is 3 pi over 2 between -pi over 2 and pi over 2? No. That's triple pi over 2. So if you take pi over 2 and you triple it, you're too big now. Because pi over 2 is the upper limit. Okay, so the answer here is no. If you were to type that in, you'll get an answer back. It won't give you an error, but it's not going to be 3 pi over 2. All right, let's try this one. is the sine of the inverse sine of 1.5 equal to 1.5? Right. So Jay, which formula is this one like, where the inverse is on the inside? Which one? Yeah, it's like 2b. So for 2b, what are you supposed to be between?
-1 and 1.
And are we between -1 and 1? No. So this is the one that if you type it in, you're just gonna get an error. Okay? Picture that graph. Picture a line at 1.5. The line would never cross the graph. That's impossible. And the last one. Same setup as the one above it, except this time the argument is 0.6. Right, so, Ian, would that, if I were to type that in, would that one work? Yes, because 0.6 is between -1 and 1. Okay. Not going to practice as many when we do the cosine and tangent formulas, but for sine, I at least wanted to go through 2 of each formula. Okay. You don't have to know that this is called Formula 2a. It's just if you want to look it up in your book, that's what they call it. That's just our book. That's not like a general thing in math. Right. Okay. Any questions on that? All right. Let's take a look at this one. So we gotta have one version where the inverse is on the outside, one version where it's on the inside. Okay, when the regular is on the inside, you can think back to what we learned yesterday. What did we say we had to be between yesterday when we did the cosine function? It wasn't -90 to 90. It was 0 to 180. That's in degrees. If you're doing it in radians, that's 0 to pi. Now, when you switch it and you put the inverse on the inside, then you can think of it like this. You can actually draw out cosine and look at how high and low it goes. Anyone have a guess at how high and low that function goes? Make it a little bigger. Yep, it goes as high as 1 and as low as -1. So the fact that the cosine function goes as high as 1 and as low as -1, that's why this is 1 to -1 again. Now, when I graph sine, if you looked at this one and you looked at sine separate and you've never seen them before, you might think, oh, they look the same. They're not exactly the same. They both go up and down the exact same amount, but they are a little different. So now you're looking at a picture of sine and cosine at the same time. How would you describe the difference between the two of them?
Sine goes through the origin.
Okay, so yeah, the sine graph does go through the origin. Another thing you could say is basically one of them is shifted to the left or to the right, depending on which one you're talking about. But it's a horizontal movement, left or right, between the two. But other than that, they are pretty similar. All right, so let's look at a couple of those. Thanks. So first one, for example 2. Is the cosine of the inverse cosine of 0.95 equal to 0.95? Right. So Alana, what do you think of that one?
No idea.
So which formula does that one look like?
Don't have an answer for you. 4B.
4b. How do you know that?
Just right them.
Yeah. Cosine is on the outside, cosine is on the outside. Inverse cosine is on the inside, inverse cosine is on the inside. What does it say we have to be between for formula 4b?
-1 and 1.
-1 and 1. is my number between -1 and 1?
Yes.
Yeah, 0.95. It's close to 1, but as long as it's less than or equal to 1, it still works. Okay. So the answer there is yes. Okay. Let's look at this one. Okay, so just one of each type is set. Is the inverse cosine of the cosine of 210 equal to 210? About Olivia, which formula is that? Yeah, that's 4a because inverse is on the outside. Inverse is on the outside. So what are you supposed to be between for that formula? And is the number that I gave you between that? So the answer here is no. That does not work. So any questions on that one? All right. So let's take a look at the last one for tangent. Okay. So here, inverse tangent, regular tangent. Don't write that in your notes because you need to be able to read it, so don't cross stuff out. But those cancel each other out, and the answer that you get is whatever you typed in, as long as you are between. How about Ray? What two numbers do we have to be between that we talked about yesterday for tangent?
90 or -90.
Yep, -90 and 90. Just remember the difference today is that you can't, or with tangent, is you can't equal -90 or 90. Okay. All right. Any questions on that? So let's look at formula 6b. Now, for formula 6b, what I keep doing is I show you a graph, and then I ask you how high and low it goes. I'm going to show you a graph of tangent, which is not a wave. It's a little different. Looks like that. So there is a pattern to it. Like sine and cosine, it repeats itself. But how high and low do you think that graph goes?
Infinite.
Yeah, it does. You can zoom out, but the more you zoom out, it's just going to keep going up and down forever. So because it goes up and down forever, basically this formula always works. You can't find a value that would make it not work. So if you get a problem where the inverse is on the inside for tangent, you shouldn't even think about it. You should just write yes, works. So here's one, tangent of the inverse tangent of 30.4. Would that equal 30.4? Yeah, the inverse is on the inside, and that's formula 6b. So the answer here is yes. Now, the other way you could see a question like this written is if I said, simplify. If I write simplify and give you an expression like that, don't write yes. Simplify means I want to know a number. So if I asked you to simplify that, what would be the answer that you would put where the question mark is? 30.4. Okay. So if it says simplify, you got to tell me a number. I wouldn't give you a simplify one that you can't do, because then you can't simplify it. I'd give you one that you could do. Right? So it's pretty easy. Just copy that number down. Right? But the way I had it, it was more of a true, false, or yes, no question originally. Okay. All right. So any questions on 3.1? Okay. So now let's take a look at the last section. Okay. So last section is on right triangle trigonometry. And the big idea in the section is that eventually you're going to have a triangle, and you're going to have to tell me how big all the sides are and how big all the angles are. That's the goal. I have to give you some information to start with. There's 3 sides and there's 3 angles in a triangle. Well, based on the title of the section, what does that mean? If we're all only dealing with problems that are right triangles, means you always know something automatically. Yep.
One of the angles.
which is it's how much? Yep, one of the angles is 90. Let's go over a couple other things with right triangles. If you have a right triangle and you have an angle that's 90, you also have something else in the triangle. It's always across from the 90. It has a special name. What's the name of the thing, the side that's always across from 90? The hypotenuse. So you have a hypotenuse. And what are the other two sides called? They're the short sides. The legs, yep. So I think that covers everything we just said. So, right triangle, triangle with 90-degree angle. Hypotenuse is the long side, legs are the short side. So every problem we do this week, that's how the triangles are going to be set up. Not next week, because next week we're going to look at the graphing. So we're going to draw sketches next week. But the week after that, we're going to come back to the same thing. We're going to look at triangles, and we're going to find sides, and we're going to find angles. But the difference that week is going to be, all your triangles are going to be like that. They won't have a 90. Okay, when you don't have a 90, there's certain things you're going to learn this week that you're not allowed to use. Some of the things I'm going to teach you only work if you have a 90. Let's talk about this term. So this comes up a lot. This and that, the two angles that I just checked off, are acute angles. What's the definition of an acute angle? Okay, it is less than 90, but I can think of an angle that's less than 90 that's not acute. Anybody? Let's add something to that. It is less than 90, but it does have to be greater than 0. So we've talked about negative angles like -10. And what that means on a circle is you've rotated clockwise instead of counterclockwise. We're not going to be dealing with negative angles in a triangle. Okay, so they have to be between 0 and 90. And when I say between, I mean strictly between. Can't be 0, because then that's not even an angle. It can't be 90, because that's a right angle. Okay. Another thing we're going to be able to use, and this is something that only applies to right triangles, is the Pythagorean Theorem. What is the Pythagorean Theorem used for? When you what? Finding what that's missing specifically? A side. Okay? Pythagorean Theorem is used if you want to find a side. If you want to find an angle that's missing, we've already kind of talked about that yesterday. What do you always have to use when you want to solve for an angle? Yep. Yep. You always have to use inverse trig. So if you want to solve for an angle, that's what you're going to be using. If you want to solve for a side, this is one way to do it. Pythagorean Theorem. And what is the Pythagorean Theorem? Okay, so a squared plus b squared equals c squared. Now, what does that mean? Because I don't have an a, a b, or a c anywhere in this triangle. Where'd you get the a, b, and c from?
The A and B go on the legs.
Yes. So call the sides whatever you want. A, B, C, X, Y, Z, S, Q, R. Doesn't matter. But the idea is that you square one leg plus square the other leg, and that's equal to the hypotenuse squared. That's the Pythagorean Theorem. What else about triangles? Anybody think of another fact about triangles? So that's a fact about the sides, Pythagorean Theorem. How about something about the angles? Anybody know something about all the angles in a, we'll call it in a flat triangle? Yep.
All add up to 180.
Yep, they all add up to 180. Notice I kind of, was specific there. I said a flat triangle because we're studying triangles that are basically on the surface of like a piece of paper, flat. You could also study triangles that are curved. So imagine connecting like the North Pole, Boston and London. That's a triangle, but it's definitely not flat. It's a triangle that's curved on the surface of a sphere. Well, the Earth isn't exactly a sphere, but it's close enough. So it's a curved triangle. All right. That's a totally different kind of thing. It's totally different. So we're just doing stuff that's flat, which for small kinds of things works fine. Like if you were using it, like let's say you drew a triangle on a map, maybe a map of a city, small scale, and you wanted to find the distance between 2 points, and you drew a right triangle. The Pythagorean Theorem would be pretty accurate. Now, if you did that with a world map, it wouldn't be accurate at all, because lines things are curved on the surface of the Earth, so it's very different than straight. Okay. All right, so what we're going to do in a second is we're going to define the 6 trig functions just like we did with unit circle trig. We're going to do sine, cosine, tangent, cosecant, secant, and cotangent. But when we did unit circle trig, we did everything in terms of a coordinate. We're not using a coordinate this week. We're going to use a couple terms that we're going to talk about right now: opposite and adjacent, and hypotenuse. So first thing is, the way I describe opposite and adjacent, it's kind of like the terms left and right. Like if you said to somebody, which way is left in this room? Well, that's not really like an absolute direction. Up would be a direction. You can say, which way is up? Up is always the ceiling. If you consider up being against gravity. But left depends. Depends on which way you're facing. If you're facing the front of the room, left is the windows. If you're facing the back of the room, left is the door, the walls of the hallway. So that's kind of how opposite and adjacent are. They're relative to you, your perspective, kind of where you are standing. Right? So what they will always do in a triangle is they'll mark where you're standing using that Greek letter, which is theta. And everything in this picture is from the perspective of that spot. So opposite is basically the side in the triangle that's farthest away. Another way to say it is it's the side in the triangle that if you got rid of it, it has nothing to do with the angle that they put in the picture. So this side is opposite. Because if you wipe this out, it had no effect on that angle that's got the square around it right there. Opposite has nothing to do with that angle at all. It's the side that's furthest away. Now, adjacent, if you just kind of think about what that word means, what is adjacent? Yeah, right next to you. It's right next to you. They said the board is adjacent to me. It's right next to me. So adjacent is the side that's right next to the angle. And you might think, well, aren't there two sides that are right next to the angle? There are, but the one across from the 90 already has a name. That's hypotenuse. So adjacent is the side in the triangle that is part of the angle. Okay? It's right next to it. It's the side in the triangle that forms one of the sides of the angle. So basically, you get rid of this side, you don't have an angle there anymore. It's like you have this. There's no angle right there. It's wide open. Okay? So adjacent is the side that's right next to your angle. And it's the side that's not the hypotenuse. Okay, hypotenuse is more of a absolute direction. It's like saying in this room, up. I don't care which way you face. Face the front of the room, back of the room, face the window. Up is always the ceiling. Doesn't matter which way you're facing. So hypotenuse doesn't matter which angle you're using as your perspective. Hypotenuse is always across from the 90. Right, so I'm going to draw the same triangle I have, I'm just going to shift my perspective. I'm going to put theta in a different spot. And now that's going to be the spot that we would do everything from. In an actual problem, they'll tell you what theta is, right, when we start getting into solving. So let's take this triangle. And let's use that as our perspective. Okay, so now everything is, pretend like you're standing at theta. Which side would be opposite now? Yep, bottom side would be the opposite. And the height would be which side? Yes, the adjacent. So the height is the adjacent, and the hypotenuse stayed the same. So when I ask you what's the name of a side from the perspective of theta, I'm looking for you to say opposite or adjacent or hypotenuse. Okay? Not A, B, or C. When I say from the perspective of something, I'm looking for one of those three words. Okay, so now that we know what opposite and adjacent are, we can define the six trig functions using those terms. Okay, so let's start with sine. So sine is defined as opposite over hypotenuse. Cosine is adjacent over hypotenuse. Now, when I say opposite over hypotenuse or adjacent over hypotenuse, what do I really mean here? Like, what about the opposite side? Like how heavy the opposite side is, what color the opposite side is, what about it? The length of it, yeah. So it's the length of the opposite side divided by the length of the hypotenuse. Cosine. Length of the adjacent divided by length of the hypotenuse. So let's just make up two lengths. What's a unit that you can use to measure length? Meters. Inches, meters, yeah, it doesn't matter. So let's say you take 5 inches and divide by 3 inches. The numbers don't reduce there, but what does happen? Something does cancel out. Inches. Inches in the top, inches in the bottom. So what are you left with for a label? 5/3, but what's the label on that number? Joe, what do you think? No, it's not distance. No, it's not degrees. No. No, inches is gone.
Does it just not have one?
Doesn't have. Just a number. So the point is, when you do a trig function, the answer that you get is just a number. It's not degrees, it's not radians, it's not inches, it's not feet, it's not bananas, it's nothing. There's no label. Okay? The labels cancel out, and it's just the number 5/3. That's all it is. And it represents one of these trig functions. We have 6 of them. Okay? It's a length divided by a length. And tangent is opposite over adjacent. Now, once we had the 3 on the left, last week we had a method for getting the 3 on the right. Before I show them to you, does anyone remember what we did with the left to get the right? We just flip them. So the other ones are just going to be flipped. So your cosecant is hypotenuse over opposite. Your secant, hypotenuse over adjacent. And your cotangent, adjacent over opposite. Okay, and there's a trick that some people use to try to remember the 3 on the left. Does anybody know the trick that I'm thinking of? There might be more than one trick, but yeah. Yeah. Can you spell that? Like, explain what you mean? Yeah. Yeah. And I kind of wrote it with capitals and lower cases to point something out. But can you go ahead and tell us what that means?
Yeah, like SCTs or sine, cosine, tangent, like opposite hypotenuse.
Yeah. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Sakatilla. When I asked it one year, I still kind of chuckle when I remember this, but I asked, how can you remember that? And somebody said, Sacagawea. Sacagawea is not gonna help you here, but he did some other stuff, but she won't help you with this. So Sakatoa is what you want to go for. All right. So the idea is they're going to give you a triangle, like that, and they're going to ask you to find all 6 trig functions. Now, in order to find all 6 trig functions, you need all the sides. Okay. Are we missing a side here?
Hypotenuse.
Yep, we're missing the hypotenuse, so then that's the first thing we have to find. Okay. You could do some of these trig functions. In fact, you could do 2 of them right now. But to do the other 4, you're going to need the hypotenuse. Okay. So how about, Edma, how do we get the hypotenuse if we know the other 2 sides? Yep. And can you set up the Pythagorean theorem here for me with, you can pick a letter you want for your variable and then the 2 numbers? Yeah, and just use those numbers. 3 squared plus 4 squared equals c squared. Okay, so she's calling the side c. All right, so let's do that out and see what we get. What's 3 squared? 9. And 4 squared? 16. So add that up. Get 25, which means c here is what? 5. Okay, so now we've got the hypotenuse. Now it didn't happen this time because I picked nice numbers, but you could get a square root. If that comes out to a square root, the hypotenuse, there are some formulas here that have hypotenuse in the bottom of a fraction. You can't leave square roots in the bottom of a fraction. Okay? So the same thing that happened last week could happen this week. You just have to fix the square root in the bottom. Okay? But it won't happen here. All right, let's go through all 6. And keep in mind, everything is from the perspective of theta. That's where you're standing when you're trying to determine opposite and adjacent. Right? So Dennis, what would the sine of theta be in this picture?
So it would be 4/3.
Yep, 4/3. And Sadie, my cosine? So what's our definition for cosine? Adjacent over hypotenuse. So that's opposite over hypotenuse. Wait a minute. Yeah. Did you say 4/3?
Yeah.
Sorry, I didn't catch that.
No, it's 4/5.
4/5.
Yeah.
Opposite over hypotenuse. And then cosine is 3/5. So adjacent over hypotenuse. And now, how about Michael? What's my tangent?
4/3.
Yep, 4/3. And Larissa, now that I have those 3, what can I do with them to get the other 3? Just flip them. So my cosecant, 5/4, secant, 5/3, cotangent, 3/4. And that's it. Now, what we just did there was not actually figure out any angles. Okay? What you did is you described a bunch of things about the angle. You described the sine, the cosine, the tangent. Any one of these 6 facts I could use to now find this angle. Okay? That's going to be the next step tomorrow. Any questions on just writing those 6 down? All right, so let's try looking at this. Okay, so the last thing we're going to look at is called the Complementary Angle Theorem. But first, just a couple terms we got to go over. What are complementary angles? So they both have to equal 90.
When you add them together.
So it is something with 90, but it's that they have to add up to 90. They don't have to equal, they could be like 10 and 80 or 45 and 45. But they're 2 angles that add up to give you 90. Now, why is this true? The 2 acute angles in a right triangle, so if I draw this out, this one and that one, always have to add up to 90. Even if the triangle looks more like this.
30 equals 91, so the rest have to be 90 to make 180.
Yeah. So if you already get 90 here and they all have to add up to 180, then the other 2 that I just circled have to be 90. So those 2 angles will always be complementary. Keep that in mind. So that kind of gives you a quick way to find the other angle. A lot of people, if I do something like this, they say, oh, I just have to add up 90 and 10, and I get 100, and subtract that from 180, and that means the top angle is 80. Yeah, you can do it that way, or just subtract that angle from 90. 90 minus 10 is 80. Okay. Right. So, the next term we have to look at to describe what's called the Complementary Angle Theorem, called cofunctions. So cofunctions are a different way to match up trig functions. So far, we've been matching them up like this. Sine goes with cosecant, cosine goes with secant, tangent goes with cotangent. When you match them up that way, those are called reciprocal. You flip one to get the other. Well, cofunctions basically match up a trig function, and then when you put the word co in front of it. So sine, and then put the word co in front of it. Cosine. Those are called cofunctions. How about secant? What would be the cofunction for secant? Cosecant. And then you have tangent, and what would be the cofunction for that one? Cotangent. So those are the 3 pairs of cofunctions. Tangent and cotangent are actually both cofunctions and reciprocals. You flip one to get the other, and they are what we call cofunctions. The 2 above it aren't like that. Okay. So any questions on those 3 pairs? All right. So, last thing we need to describe that theorem is this diagram. When we draw right triangles, you can draw them however you want. You can have it face this way, you can have it face that way. It doesn't matter how you draw it. In fact, it doesn't even really matter what letters you put where. If you want to pick X, Y, and Z instead of A, B, and C, you could. But what you have to remember in a triangle is that a certain side has to go across from a certain angle. Always. Certain sides have to go across from certain angles. And we use letters that help us to remember which side goes across from which angle. Right? So the way we usually try to remember it is A, B, and C are your sides. And we always use English letters for the sides. For the angles, we'll use Greek letters. Now, some textbooks use English letters for everything. They use like a lowercase a, b, and c for the sides, and a capital A, B, and C for the angles. That can be confusing. Because if you asked me a question, you said, well, what is A? How did you figure out A? I'd have to say, which A do you mean? Do you mean the lowercase a or the capital A? Which one are you talking about? And the other thing that can get confusing is some letters look the same when you write it capital or lowercase, like O or C. Letters like that. A and B look different, capital and lowercase. But we're just going to avoid that whole problem and use Greek letters for angles, English letters for sides. Does anyone know the name of this Greek letter in the lower left? Yep. It's alpha. Alpha is the first letter in the Greek alphabet. It goes across from the first letter in the English alphabet. A goes across from alpha. And how about the Greek letter up at the top? Anybody know what that one is? Yeah. It's beta. Second letter in the Greek alphabet goes across from the second letter in the English alphabet. B goes across from beta. A goes across from alpha. If you want to use other letters besides A, B, and C and alpha and beta, you can. You just have to somehow keep track of which side is supposed to go across from which angle in your diagram. But that's the easiest way to do it. Most people do it that way. All right, so let's write a couple things down, and I think you're going to see a pattern, and that pattern is going to be this theorem. Okay. Let's write the sine of alpha. Okay, it's not going to be numbers. It's just going to be letters. So alpha tells you your perspective. I want you to do everything from the perspective of that angle. And I want you to find the sine. So Tyler, what would the sine of alpha be? Yeah, A over C. And by itself, that's not very interesting. A over C. Now what I'm going to do is first write the cofunction of sine. Ian, what's the cofunction of sine?
Like, do you want the fraction?
The word. The cofunction for sine.
Cosine?
Cosine, yep. And Jay, what angle is complementary to alpha in this picture? Beta. And I'm going to find that in a second. So I did two things. One, I found the cofunction of that. Two, I found the complement of that. And I wrote them right here. Cofunction of sine is cosine. The complement of alpha is beta. And Dennis, if I find the cosine of beta, that's adjacent over hypotenuse. What side is adjacent to beta?
C. That would be A.
It would be A.
Yep.
And adjacent over what?
B. No, C.
C.
Yep.
So cosine is adjacent over hypotenuse, and that's A over C. And what do you notice about the answer you got here and the answer you got before? They're the same thing. Cofunctions, complementary angles. Try one more. Let's pick tangent velocity. Okay, so Sam, what would be the tangent of alpha? Yep. Opposite over adjacent, and you're doing it from alpha. A over B. Now, let's do exactly the same thing we did up above. Sheridan, what's the cofunction of tangent?
Cotangent.
Cotangent. And what angle is complementary to alpha?
Beta.
Beta. So, cotangent is adjacent over opposite. Kyle, what side is adjacent to beta?
A.
A. And what side is opposite?
B.
Came out exactly to the same answer again. Cofunctions, complementary angles. And that's going to keep happening. If you check, you can keep checking all of them, but they're always going to come out the same if you compare cofunctions and you compare complementary angles. And that's the complementary angle theorem. Very simple description. Cofunctions of complementary angles are always equal. They always come out the same. So instead of trying it with just alphas and A, B's, and C's, let's try it with numbers. So what I want to do is find something that's equivalent to the sine of 30 using what I'm saying right there. So what's the cofunction of sine? Cosine. And what's the complement of 30? 60. So the sine of 30 should come out exactly the same as the cosine of 60. Let's see. So there's the sine of 30, 0.5. Here's the cosine of 60, 0.5. They're exactly the same. Right. How about tangent of 15? What, I'm not going to take this one in, but what would that come out the same as? 75 is the complement, so that's that part of it. And the what of 75? The what? The cofunction, which is cotangent. Yep. And how about secant of 40? What would that be the same as? Cosecant of 50. Okay. So you might be wondering, like, well, how does that really help you do anything? You're just finding something else that it's equal to. And it would help you in a problem like this. So this is a problem where the directions would say simplify. So I'm looking for a number. And then I might ask you to explain like how you got that. Look at the function that's in the top, sine. The one that's in the bottom, cosine. What are sine and cosine? They're cofunctions. Now, look at the angles. 15, 75. What kind of angles are they? They're complementary. So you have cofunctions of complementary angles. So what does that mean about what's in the top and what's in the bottom? Yeah? They're the same. I don't know what the sine of 15 is. That's a hard one to do in your head. I have no idea what it is. And I have no idea what the cosine of 75 is. But whatever they are, that value in the top and that value in the bottom are the same. So what does that mean you'd get when you do that? 1. You don't need to know what the sine of 15 or the cosine of 75 is to do that problem. All you have to know is they're the same. And if you divide two things that are the same, you always get 1. Right, let's look at this one. Tangent of 12 minus the cotangent of 78. How does the value tangent 12 compare to the value cotangent 78? What's complementary? So the angles are complementary.
Yeah.
So you could say that. Well, what about the functions? What are they? So how does this entire value compare to this entire value? They're the same. That's the point. They're the same. What is the tangent of 12? I don't know. No idea. What's the cotangent of 78? I don't know. But I know they're the same. So what does that mean I would get when I do that? 0. So it works if you divide two things that are the same. You get 1. Or like if you put a negative in front of it, what would the answer be now? Now it'd be -1. Still the same idea. Would it work for addition? If you add two things that are the same, do you always get the same thing? What happens if you add two things that are the same? What do you get? Compared to what you started with? You get what?
Twice what you started with?
Yeah, you get twice what you started with. Well, twice what you started with is different depending on what you started with. Here, I don't care what you start with and what you end with. If you subtract two things that are the same, you always get 0. How about multiplication? If you multiply two things that are the same, you always get the same thing. No, you get that thing squared. So this trick does not really help you with multiplication or addition, but it does with division and subtraction. Okay. Any questions on that? All right. So tomorrow we'll take a look at the last part of 4.1, which is actually finding all the sides and all the angles in a triangle, and that's where we're going to see the connection with inverse trig. Okay. So first part of the homework is 187. 46 to 51, 53 to 55, all. Those questions are all yes or no. And then 9 to 21 odd is the kind of stuff we just did at the end of the lesson. Okay. Don't forget, I will have extra help on Thursday. So if there's anything you got to finish up, that would be the day if you have to come after school to do it.